Go.
Welcome to Out2.
Hello and welcome back to Out2. This is section 6.10 on hyperbolic functions. We're going to wrap up chapter 6 and have that exam in 2 days that you want so much, right?
I'm scared.
Good. So the hyperbolic functions. This is going to be a new bunch of functions. You hopefully know about polynomial functions that also encompass constant function, linear function, quadratic, cubic, and all of the other polynomials, right? Then you have radical, rational, logarithmic, exponential, trigonometric functions. So you learned a whole bunch of different functions along the way, whether it was pre-calculus or algebra. Now we are learning the new type of functions, and whatever pre-calculus rules you learned that apply to all functions would apply to hyperbolic functions as well. Now, the interesting development for these hyperbolic functions, one of the mathematical gods, Leonhard Euler, was the one who figured this out, and he figured it out by just, by the virtue of playing with expressions, which is amazing. So he was the most productive mathematician of all time, and he published and discovered pretty much all of the mathematics we have. So if you're interested in all of his works, there is a bundle called Opera Omnia, which is $11,000 to purchase because it has almost 100 books, and each one is about 2,000 pages of his collected works. So you figure out how much work and new stuff he developed for his lifetime, and for the most of his life he was blind. So he would sit and he would dictate this mathematics to a whole bunch of scribes, and they would just be writing and then verifying and publishing papers. So yeah, very interesting fellow. Now this is what happened. At one point in his life, he figured out that he can write the sine x function in terms of exponential function and write it as e to the ix minus e to the negative ix divided by 2i. And that's I, the complex I. I is the square root of negative 1. And he also figured out that he can get the cosine x as e to the ix plus e to the negative ix over 2. So these are the two formulas that he discovered, and they really worked well to, solve problems, either way, using either ease or trig. And then he asked himself a question. He asked himself a question: what if I remove all i's? Yes?
Is there an I in
No, just sine has I, cosine does not have I. So then he asked himself a question, and that question was, what happens if I remove i's? What happens? And he develops the entire branch of hyperbolic functions with all of the stuff. So technically that's where the hyperbolic functions come from, right? So now the definition for sine hyperbolic x is equal to e to the x plus e to the negative x, minus e to the negative x, and then cosine hyperbolic x is e to the x plus e to the negative x over 2.
This is one of the quiz we didn't learn yet.
So, see, we'll learn ahead. So now these are the two definitions that he discovered, and the reason why he called these hyperbolic trig functions is because they behave as if they were trigonometric functions, but they're not. See, the biggest thing that separates the world of trigonometry and the world of hyperbolic functions is that trigonometric functions are periodic. You have a period of 2 pi for sine or pi for tangent, and then the function will repeat itself the same way after that period expires and the new period begins and the new period. So it's just like you have a period of a week, right? So that's 7 days, and when that passes, you have another period of 7 days, and you have another period of 7 days. That's a trig function. Hyperbolic functions are not periodic. And because they are not they're not periodic, right, then they can be anything like trig functions. However, some of the properties, because the definitions are so close, some of the properties for hyperbolic functions really remind of the trig functions, and actually it makes sense to call them sine hyperbolic and cosine hyperbolic, and then the other 4, tangent hyperbolic, cotangent hyperbolic, and so on. And you'll see that all of those definitions are pretty much the same as in a trig, and some of the fundamental identities are the same, but the majority of identities are what we would say close enough, right, without being the same. Obviously, if everything was the same, then it would just be trig, right? So they're different enough to create their own realm. And then they have their own realm of application as well. So again, you have to have non-periodic function to describe situations that are different than the situations that the trig would describe. So now we have these two basic definitions, right? Maybe I should be more dramatic in boxing this because this is the essence of what you must know, right? And then we move on to define the other 6. So tangent hyperbolic x is going to be sine hyperbolic x divided by cosine hyperbolic x. And if you want to use the e definition, so that's e to the x minus e to the negative x divided by e to the x plus e to the negative x. So that's the first, right? And then you have the cotangent hyperbolic x, which is going to be cosine hyperbolic x divided by the sine hyperbolic x, which will be e to the x plus e to the minus x divided by e to the x minus e to the negative x. So these are our 2 functions. And now we have secant hyperbolic x to be 1 over cosine hyperbolic x, which would be 2 over e to the x plus e to the negative x. And finally, cosecant hyperbolic x is going to be 1 over sine hyperbolic x, which is 2 over e to the x minus e to the negative x. So these are the hyperbolic functions definitions. And as you can see, this is just going to be some kind of a combination of e to the x and e to the negative x. If I need to compute a hyperbolic function, let's say tangent of 3, your input 3 is not an angle, 3 radians or 3 degrees. Your input 3 is the same 3 that is input for x squared, right? Because you are actually placing that 3 for these x's in exponential functions, and then you are using those to compute. So how much is sine hyperbolic of 3? Well, that's going to be e cubed minus e to the negative 3 divided by 2, and that's going to be some decimals. Right, so you can actually, punch that in a calculator and see what we get. So let's take a look at that calculation. We have open parenthesis e cubed minus e to the negative 3 close parenthesis everything divided by 2. And I have 10.017, so I'm just going to put 10. It's good enough. 0.02. All right, sorry. Well, there we go. All right, so this is our calculation for, the way you compute things. Maybe I'm going to box these as well because these are all definitions, even though they're all spin-offs of sine and cosine. So now, as I mentioned, these guys are similar to trig functions. They might have some trig-looking identities, which we're going to call hyperbolic identities, and they do. So let's take a look at hyperbolic identities. So for hyperbolic identities, we have a whole bunch of them. Let's write the cosine hyperbolic squared minus sine hyperbolic squared is equal to 1. So cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. For trig, that's sine squared plus cosine squared, right? Then we have 1 minus tangent hyperbolic squared x is equal to secant hyperbolic squared x. That's close. And finally, cotangent hyperbolic squared x minus 1 is cosecant hyperbolic squared x. We have the even and odd properties. So even and odd properties say that the cosine hyperbolic of negative x is equal to cosine hyperbolic x, which means that's the even function. Then we have sine hyperbolic of negative x is equal to negative sine hyperbolic x, that's odd. And finally we have tangent hyperbolic negative x is equal to negative tangent hyperbolic x, that's also odd. So even and odd functions work with the exponents, and eventually in chapter 9 we will be back to discuss briefly hyperbolic functions, and this would be even clearer, the connection between trig and hyperbolics. Now we have our cosine hyperbolic of x plus y, so when you add two values, it's going to be cosine hyperbolic x, cosine hyperbolic y, and we keep the plus with the sine hyperbolic x and cosine hyperbolic, sine hyperbolic y. And we have sine hyperbolic x plus y would be sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. Then we have the double angle identity. Cosine 2x is equal to sine hyperbolic squared x plus cosine hyperbolic squared x. You did not expect this one. Because look, wouldn't that be if it was a trig that was equal to 1? Right? So now you actually see that these formulas are kind of reversed, actually. If you know your trig, this formula is the same. If you remove ages for sine hyperbolic x plus y, if you just remove age on each one of these, you will actually get your trig equation. Right? But over here, it has a wrong sign for trig. That's a minus there. Now, between the cosine it's supposed to say cosine hyperbolic 2x. Between the cosine hyperbolic 2x and a cosine 2x, see, cosine 2x has the formula that it's like the first one. Cosine squared minus sine squared in trig is cosine 2x. So these formulas are swapped now, actually. So what used to be the cosine of 2x is now giving you 1, and what used to give you 1 is now giving you 2x. So they're swapped. That just depends on how much you know your trig. Now you have sine hyperbolic 2x, and that's identical to what you have in trig, 2 sine hyperbolic x cosine hyperbolic x. And then cosine hyperbolic square x, this is the power reducing, is cosine hyperbolic x plus 1 divided by 2. And for the sine, you're subtracting 1. So cosine hyperbolic squared sine hyperbolic squared x is equal to cosine hyperbolic of 2x minus 1 over 2. Forgot the 2 over here. 2x. Fix the cosine formula. It's supposed to have 2x in there. Fix the cosine. It's 2x in the equation. So these are the hyperbolic identities, and as you can see, they are very, very, very close to the ones that you have for trig. So if you are looking at, the trig, that will be equation for cosine 2x, which is swapped with the one below. This one should have a plus, not a minus. This one should have a plus, not a minus. These are the same. This one should have a minus instead of a plus. This is the same. And then this one should be swapped with number 1. And then this is the same. And then these two are the same. You just need to swap the terms in the numerator. And that's that. So as you can see, the majority of the formulas are the same, except now using hyperbolic. And then those that are not the same, they're very close to what you had before. So the biggest issue, right, is that this formula and this formula are completely opposite of what they actually used to represent, right, for the pre-calc. Now, one of the exam questions could be to prove any one of these identities. And the way you do this is you just replace your e's and you just shovel the algebra. So I'm sorry for disappointment and the lack of calculus in that. All you do is you shovel algebra as you go. So I don't know, pick one of these. Let's do one. Cosine squared hyperbolic, right? So you're this one, right? Yeah. All right, perfect. So let's prove that the cosine hyperbolic squared x is equal to cosine hyperbolic 2x plus 1 divided by 2. All right, so what do we know? We know that the cosine is given to us as e to the x plus e to the minus x over 2, and that needs to be squared on the left-hand side. On the right-hand side, I have e to the 2x. So e to the 2x plus e to the negative 2x over 2 plus 1 over 2. So all I did is I subbed. As I said, all of the identities that I have there in blue, they're all solved by immediately replacing every sine hyperbolic and every cosine hyperbolic with e's. And now you're just supposed to shovel through this algebra, right? So what do we have on the left-hand side? On the left-hand side, as I square this, I get e to the 2x, and then I have the, this is a square of binomial, so middle terms die, and then we have plus e to the, no sneezing, negative 2x, what did I just say, over 4. Equal to, it was a good effort though. On the top equation, I'm going to multiply numerator and denominator by 2 to get rid of the double fraction. So as soon as I multiply that by 2, the 2 will cancel. And, oh wait. No, that's not good when I FOIL it here. E, there is a 2 in the middle, because the middle term is 2ab. So that's 2 times A is e to the x and b is e to the negative x. So this works out to be 2e to the x minus x, which is 2e to the 0, which is 2 times 1, which is 2. So the middle term is 2. And then you have plus e to the negative 2x. There we go. My algebra is rusty. I haven't used it since 10 a.m. this morning. Now, on the other side, we have e to the 2x plus e to the negative 2x plus 2 divided by 4. Same. Done. Right? They're the same. So to solve any of the identities, you write out the identity, then you plug in your cosine hyperbolics or sine hyperbolics, whatever you need to do, and then from there you just shovel through algebra. So none of these identities, they're just like the identities you had in your trig, except now you are shoveling e to the x rather than trig functions. How about you work on one? Yeah.
We'll just be plugging in like definitions of cosine, like just like the first 6 definitions, basically is all we plug in.
Just 2, just sine and cosine.
Oh, then, yeah.
Because the tangent can be expressed as, all the other 4s can be expressed in terms of sines and cosine hyperbolics. There is no need to memorize those e values, right? Can you? Yes.
I was going to say, so basically, like a question that you did have in the exam would be, you would give us the formula.
Yes.
And then we would plug in, so we don't need to memorize the whole, like, identity.
The setup, no. You don't have to memorize all of the identities. Those of you that are interested, obviously, you will find a way to deal with this in terms of, the similarities with the trig. But, the formula, the identity formula will be given to you, the one that you need to prove. And you just go and prove it.
Plug in for the sine and cosine or whatever.
Yes. Plug in the sine and cosine and then shovel through algebra. I hope you're not disappointed. Yes. Not for this one. But get them in fast. I mean, when? Like yesterday. Right?
Yeah. When'd you come?
He's a ninja.
I literally made an announcement of you not being here.
Did I miss much? When did you guys start? Yeah, bro.
We always start late, bro.
We started at 3, yeah. It's a very long lecture.
Just wrapping up now.
My fault, bro. Back up.
All right, so do a proof of another one, or this is sufficient?
This is pretty good. Another one's pretty good. Harder one?
Which one?
I know the hardest one.
Yeah, which one do you think would be the most difficult?
What did we talk about earlier? Like, what do I think is? They're all equally a joke.
Which one do objectively has the most amount of algebras?
All of them.
Probably the one we just did.
What minus cotangent? Yeah, cotangent h squared x.
Cotangent? Okay. Prove that the cotangent hyperbolic squared, right, minus 1 of x, is equal to the cosecant hyperbolic squared x. I tried this one on your own for about 25 seconds. That's what you get.
Can you open up the homework before the test starts?
Yes.
Is there a 6.8 homework, like online? Are there like homeworks online past 6.7?
Not yet.
Okay. So like when
Now.
like today there were okay. They just do like, I guess, 40 minutes or whatever.
He said so, so you know he's in charge. Stop dancing around and play. Do the.
I looked for my pen, but I found it. You gotta relax. Yeah, my boy Despicable Me, you hate it. Do everything.
Never.
Never. You go on YouTube and write all the mean comments, right?
The best comment I ever got was on Rate My Professor. A student told me, said, "This guy will show you no mercy."
Oh, like 6, 7 years ago when I was
Where are you now?
Oh yeah, I've upgraded to God. I told you.
To me, you're my comrade. That's okay.
There's good references right there.
I know, but like, I got it wrong.
Well, I did just when I was years, you know. I had to go to the post office.
It's something that Europeans of Paris won't take. It's the post office.
My friend has got these. Got these.
Oh, it's all
Like in person, it was a lot more.
So you have some of the denominators, right, and stuff. All right. Oh, you went even with the substitution. That's some next level stuff. Like, okay. So what is the cotangent in terms of sine and a cosine? The cotangent is the cosine hyperbolic squared x over sine hyperbolic squared x minus 1 is equal to 1 over sine hyperbolic squared x. The entire equation over here times sine hyperbolic squared x, right? And then that gets us to cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. That's already established identity, so technically you are done if you write 1 equals to 1. But then, okay, let's not be cheap, all right? Let's not be cheap because, right, that's the established identity already. You see that? So we're done. But let's just, let's push, right? So we have e to the x plus e to the negative x over 2 squared minus e to the x minus e to the minus x over 2 everything squared should be 1. Square the first one. E to the 2x plus 2 plus e to the negative 2x over 4 minus e to the 2x minus 2 plus e to the negative 2x over 4 should be 1. So now e to the 2x and negative e to the 2x, positive e to the negative 2x and negative e when the minus distributes, right? So all it's left is 2/4 minus negative 2/4, and 1 is equal to 1 now. Because what you have there is a half plus half, which is 1. Bueno? Now these guys are functions. That means all of the stuff that functions have, guys, domain, range, graphs, x-intercepts, y-intercepts, all of that stuff. You spent the pre-Calculus 1 learning basics of functions. All of those basics are going to play for each one of these 6 that we are defining now. Now, we really don't have time to go through every single detail. What would be a very worthwhile exercise for all of you is to look into the graphs of these hyperbolic functions for all 6 of them and see what they look like to kind of have an idea where to apply them. I will give you one application for hyperbolic cosine. So when you have those power line towers, and you stretch cables between, and they keep going past these guys, the equation for a cable that it's hanging is given by the hyperbolic cosine. So it looks like it's x squared. It's not. It looks like it's a parabola because all you see is this kind of shape, which is stretched over, right, the long distance. But it's not that kind of shape. It's actually cosine. So y equals a cosine hyperbolic bx, right, would be an equation that would model the cable or the cord. Now, for electrical engineering, this is insanely important because what happens when the wires get cold? In the winter, there is freezing rain, there is ice, there is snow, there is cold. What happens with things? They shrink. So if you don't have slack between two, right? Every time you drive around, just take a look at power lines. Every single power line has a slack on. Why? When it gets cold, they flatten a little bit. They don't go flat completely because that introduces extra tension, right? But they kind of lift up, right? So if there was no slack, if they weren't hanging a bit, which is creating the cosine hyperbolic equation there, it would snap. Every time it's cold, it will snap. So we need that, right? But you can't just eyeball it and say, yeah, it's good, right? Because what happens in 100-degree weather? It expands, and then if you have a truck pass underneath, right? Yeah, rips them off. So there are very delicate calculations that have to be done. And the inverse cosine, the cosine hyperbolic is the equation for that kind of stuff. One of the project questions that I have is actually on computing that. It actually takes about $100,000 to set up one side for these big power lines. Very, very expensive. Very expensive stuff. Look into graphs of all 6 hyperbolic functions. Calc of hyperbolic functions. We have derivatives, we have integrals. If you have a limit, you invoke your E definitions and then you just work out the limit, right? So limit is not an issue. There is some stuff to cover for integration. And yeah, I'll write it, but let's first take a look at page 494, where they give you all of the derivatives and all of the integrals. We know the integrals are antiderivatives, right? So observe that there is no minus sign going to sine to cosine, cosine to sine hyperbolic in any order, any way you go. No minus signs whatsoever. The one that gained minus sign and didn't have it before is the secant tangent one, right? So now you still have pairing, calculus pairing, and we will deal with this a lot when we get to trigonometric integrals and trig sub in chapter 7. That's next week, guys. We will deal with the trigonometric pairing for calculus, which is sine with cosine, tangent with secant, and cotangent with cosecant. Those are the trig pairs, calculus trig pairs. Now, for hyperbolic functions, you see that those pairs are preserved. Sine hyperbolic is with cosine hyperbolic, secant and tangent, and cosecant and cotangent. The only thing that is now different is that the minus sign that used to be with one of the directions for derivatives of cosine is now with the secant. So these guys are so close. So generally, if I put the integral of cosine hyperbolic, one of the most common mistakes is for someone to write negative sine hyperbolic because in derivative of cosine is negative sine, but the derivative of cosine hyperbolic is a positive sine hyperbolic. So you have to be careful and mark those differences, right, so that you don't get into those problems. So what do we have? We start with all of these. So I'm just going to write all of these. Oh, and note that they're the same. Right, the tangent goes into secant squared, the cotangent in cosecant squared, sine with the cosine, cosine with the sine, and then sine hyperbolic. Sorry, secant hyperbolic has secant tangent, right? I mean hyperbolic secant and hyperbolic tangent. So these are identical to the trig integrals, except for that those two formulas swapping where the minus is. So let's write these. We have the derivative of sine hyperbolic x is cosine hyperbolic x, which means that the integral of cosine hyperbolic x dx is sine hyperbolic x plus c. The derivative of cosine hyperbolic x is positive sine hyperbolic x. And then finally the integral of sine hyperbolic x is equal to, oh, I forgot dx. That's terrible. Plus c. There's your screen. Oh, thank you. So we have the next one for the tangent hyperbolic x, which gives us secant hyperbolic squared x. That means that the integral of secant hyperbolic squared x dx is tangent hyperbolic x plus c. So whatever you write in the left column, it will be just written reversed in the right column for integration. So now we have three negative ones. Next one is the cotangent hyperbolic x, which is going to be negative cosecant squared x, and that's the integral of cosecant hyperbolic squared x. I forgot the hyperbolic over here. Holy nightmare. So cosecant hyperbolic squared x dx is going to be cotangent hyperbolic x plus c. Two more. The derivative of secant hyperbolic x is negative secant hyperbolic x tangent hyperbolic x, and then the associated integral can't fit here with the secant hyperbolic x tangent hyperbolic x dx is going to be just the secant hyperbolic x. The last one is for the cosecant. So the derivative of the derivative of the hyperbolic function to the cosecant. So we have the same happen, negative cosecant hyperbolic x, and then what's the pair? This is cosecant. Cosecant gives us so cotangent hyperbolic x. Good. Oh, I didn't write the integral. Integral of cosecant hyperbolic x cotangent hyperbolic x dx is equal to negative cosecant hyperbolic x plus c. So there they are. All of that stuff is for calculus of these hyperbolic functions. What are the favorite methods of integration here? Well, u sub, and then as we progress through the course, integration by parts, right? And well, that technically u sub integration by parts. So now they say integrate sine hyperbolic cubed x times cosine hyperbolic x dx. The limits are 0 to ln 3. Go.
Yeah.
So what is the way to do this integral? U sub. What is U? Sine hyperbolic. Very good. So integrals are going to be done using U sub. U equals sine hyperbolic x du equals cosine hyperbolic x dx. So the integral changes into u cubed du. Now the only thing I have to do is I have to flip the limits, right? Because now the entire integral is supposed to be in terms of a u variable. So let's do that in blood over here. So u1 is e to the 0 minus e to the 0 divided by 2, and that's 0. So the bottom limit remains 0 because sine hyperbolic of 0 is 0. Now u2 is going to have e to the ln 3 minus e to the negative ln 3 divided by 2. Now this is something that we actually have to compute. So now we have e to the ln 3, that's just a 3. And then minus. And now this becomes, the negative goes inside, makes 1 over 3, so it's a 1 over 3 here. Times 3, top and bottom, to get 9 minus 1 over 2, which is 4. So the limits are changed from 0 to ln 3 to 0 to 4. And then we also have the integral, which changed. So now we integrate this We're done with hyperbolic functions. There's nothing hyperbolic on this one. It's u to the 4 over 4 computed from 0 to 4. There's way too many 4s on one spot. So when I plug in 4, I'll have 4 4s, but one is going to cancel, so that's a 64. And I plug in a 0 for u, I get 0. And the answer is 64. I know, it did take 2 lines.
It's supposed to be 2 times 3, so that's 9 minus 1 over 6.
What happened?
When they do 2.
Yeah, you got
Yeah, it should be 9 minus 1 over 6. You forgot to multiply 2 by 3.
Ah, huh. That's a 6. Well then, that's 8 over 6, which is 4/3. But good thing you're paying attention. So the limit is 4/3. So we're not done. So that changes everything over here. So now when I plug in 4/3, 1 is going to cancel, so that's a 64 divided by, that's a cube root of 64, right? Minus 0. Okay. This is 8, 2. So this is cube root of 8 squared. So the answer over here is 8 to the 2/3. I'd say it's good. Move on, right? What happened? What was your calculation?
You take 8 to the 2/3, so the cube root of 8 is 2.
So 60. You said 64.
No, I'm talking about over there. So
Oh,
the
oh.
answer is also equal to 4.
Oh,
It's the same thing.
you mean erase this? Is that what you say?
Is it equal to 4?
How can it be equal to 4?
Alright, so the
Cube root of 8
cube root of 8 is 2. Square that, that's 4.
Okay.
So that's 8 to the 2/3, right? It's the same thing.
Yes.
So it was in 4, right?
2 squared, which is 4. Yes. Yeah, I had tough time understanding what you're saying. That's good. So cube root of 8 is 2. 2 squared is 4. So the answer is 4. Good.
You're gonna roll today, bro. I guess
Ow,
you
wait.
tomorrow. Hardly know. Don't worry, bro. Tonight we're gonna be You come early? What you did last time? Sorry.
There are also 6 inverse hyperbolic functions. It's much easier for hyperbolic functions to deal with the inverse than the trig, right? Trig has to worry about because it's periodic, trig has to worry about the one-to-one and on-to conditions. I mean, all of the inverse should worry about that, but the issue for a trig is that when you find an inverse and you plot the inverse is not a function, unless you restrict the domain. Now, these guys are not periodic, so at least it eliminates that part of calculation. So there are also 6 inverse trigonometric hyperbolic functions, and they're on page 498. So I'll just list 2 that are important. The rest is so cosine hyperbolic -1. That's the notation for the inverse, right, with the -1, and that's equal to the ln of the square root of x plus square root of x minus 1, x squared minus 1. For all x is bigger than 1. And then let's write the sine hyperbolic ln of x plus square root of x squared plus 1. So those are the 2. And
What would you do? Why does it work? How does it work?
So those nested square roots, and then there's ln.
It's fun, right?
So you actually set the cosine equal to y, then you move it to the other side, and it's too much for now that you want to wrap up and do your lab and exam review.
How do you know?
Yes.
My scroll is like 6 inches.
6 inches.
That's what I was thinking. I know, it's like right there, I guess.
Upper
I
limit
just got
and
lost. Like, I tried to do a calculation for plugging in 4/3 and like it did not get.
So Robbie is not in our last
64 over 81.
Yeah, 64 over 81.
Yeah, so
Would it be 4 to the 4th?
it'd be 1/3 times 4/3 times 4/3. Or 4/3. Yeah.
It'd just be 4/3 to the 4th.
Let's just. So we have
6 over 81 over
4/3. So this is the same problem for the third time. So we have 4/3 to the 4th divided by 4 minus 0 to the 4 over 4.
Yeah, 0.
Bueno?
Yeah.
So the second one dies, right?
Yeah.
No questions asked, so we only focus on the first one. Now the first one has 4 times 4 times 4 times 4 over 3 times 3 times 3 times 3, everything divided by 4, so one of the 4s dies. So what we have is now so 4/3 0. Okay. So now what you have is 4 times 4 times 4. Well, that's 64 over 9. So 3, 9, 18, and then 54, right?
27.
No, it's 81.
27.
Oh wait, I am. Yeah, this is 80. I'm looking at the 4s. 4s are 64. So 64 over 81? All right, good. Right. Good. All right. I'll see you after the break for the review.